Today we're going to do section 5.6. So first let's scan the book. This is the page that's already scanned in the previous video, but we'll look at it again because most of it is, most of it's new stuff. Okay, I think I'll even move it a little closer and then a little closer on the bottom, but not too much. It's, that should be good enough. Okay? Next, page 172 and 173. Here we go. Now, right, that is a little closer. That's the entire page. Okay, and then a little closer on top. Let's see. And a little closer on the bottom. Okay, so that's that. Next, page 174 and 175, which we will, again, let me hold this thing steady. Okay. And then a little closer on top. And a bit closer on the bottom. That's good enough. And finally, 176 and 177. So let's look at this thing a little closer. Okay, that's about it. Okay, a little closer on top. And a little closer on the bottom. That should do it. So we're doing section 5.6 on page 170. First, please read this this first short little paragraph, introductory paragraph yourself about continuous functions, and then I will move on to the Heim-Borel theorem. The Heim-Borel theorem is says something like this. Okay, that might sound obvious to you. I don't know, but let's say we have a closed interval from A to B, all right? And then, and for each point on this closed interval, including the endpoints, we have an interval for each point. Let's call it point C, all right? So then for each point C, we have an interval of I of C that is somewhere from that's defined by delta of C. That is, the interval will be C going from C minus delta of C to C plus delta of C, where delta of C is a bigger than zero number. So that there's a range, okay? That this thing is going to be called the cover. We'll call it IC. Okay, IC is the area from C minus delta of C to DC plus delta of C. So it's a little area like this, right? It covers C, and that's called the cover. Now, if every single point is defined with a delta like that, and it doesn't matter what the delta does, as delta is, as long as it's bigger than zero. It can be big number, small number, it doesn't make any difference. So every single point from 0 to 1, we have it covered by its own delta C. Okay, so then the entire collection of stuff there, which then we have an infinite amount of stuff, right? And that is called a covering. At least that's what I call it. The book doesn't exactly define it, and that's okay. We'll just, but that's what. But what I will call it, that is each individual one, I'll call it a cover, and the collection of all of them is called a covering. All right, now next let's read this part where it says, the Heim-Borel theorem states that a finite number of the intervals, that the covering, it can be chosen that covers the entire interval. So out of all that ICs that I tell you about, which every single C has an I to it, that's overkill. We don't need that much cover. So if each point only needs to be covered by one covering, then or one or more, but at least one, but that's all it needs, then we can throw away a lot of the extras, right? And as the Heim-Borel theorem states that we can pick a finite number of coverings that will cover the entire closed interval. Now, the fact that it's closed matters greatly, okay? If it's not closed, this trick is not going to work. And we're going to see an example right now towards the bottom of the page, and then we'll have an open interval, okay, where C is between 0 and 1, but doesn't equal, the endpoint's not included. And we'll let A equal to 0, B equal to 1, and we'll define I of C, the covering for C, for each C in this interval as C over 2 to 3C over 2. All right, so that I have it written right here. See, we have each C in this interval. Now I don't include the endpoints. So each C in this interval goes at the cover goes from C over 2 to 3C over 2, okay? Now, so as you can imagine, as C moves this direction, the cover gets bigger and bigger, right? Because each cover is defined by how big C itself is from 0. So the covers gets bigger and bigger. But on the other hand, as it approaches 0, the cover gets smaller and smaller. And specifically, no matter how close you get to 0, okay, the C's that's close to 0, they, like this one right here, which is close to 0, right? It only goes from C over 2 to 3C over 2. So it's missing a little bit of the entire interval. And no matter how you look at it, okay, so as a result, then let's say that there is at this point that there is no finite collection of covering that can cover the entire open interval. I mean, this part is covered, yeah. The question is here, okay? What are you going to do with that? The reason is because let's say you have a finite interval, okay? A finite collection of covers that will cover the entire thing. In that case, where C is, of course, being that it's finite, you can arrange C in order from the smallest to the biggest. Then the smallest C, which is right here, right? The smallest C only gets to be C to the half. It still has a part that is missing. Okay, everybody's got a part that's missing. And then, so no point to the left of C1 over 2, that's the first one, is covered by the set. That therefore, it is not possible for you to have a finite collection that will cover it, because any finite collection, you're going to find a little bit that it didn't cover. Sorry, we can't do this because of the way the coverings are defined. Okay, the covering that's defined such that this part is always missing. Okay, if you pick a C in here, then you'll miss a tiny little bit inside there. Okay, everybody misses a little bit. Nobody covers 0 is basically what that means. Okay, even though you got infinite amount of covers, nobody is covering 0 or even close to 0. So it's you're out of luck, basically, is what that means. And that is why with the Hein-Borel theorem works only for closed intervals. Okay, especially this point. Well, either point. The point is that we have to include the endpoints for the Hein-Borel theorem to work. All right, so remembering firmly that the Hein-Borel theorem requires you to have a closed interval, let's look at the next page, page 171, where we look at theorem 5, which reads that, so we have C in between A and B, just like we said, right? And then in that case, and the interval is closed like it should be, in that case, there exists a finite covering. That is a finite bunch of points, C1 to Cn, which creates IC1 to ICn. Those are the covers. And together, they will cover the entire closed interval from A to B. And that is the Hein-Borel theorem. Okay, and next let's look at the proof. The proof is going to define something, okay, and to make it easier to argue. We will call a point A of the interval I accessible. Now, A is accessible if the interval from A to from the small a, the beginning of A, to our big A, can be covered by a finite sequence of the ICs. So I have this written down. Basically, I'm repeating what the book said, okay? But I'm just arguing it for myself. Please do this yourself as well, okay? And after you read the theorem, then please prove it yourself as if you haven't read it, and see if you can get it to logically come out. So this is what I did. So let A be a point, right? So I have a picture here even. So big A is a point inside the interval AB. So Accessible means that from the small a to big A, this closed interval can be covered by finite sequence of IC. Now this that is can be covered by a finite collection, right? Now this is first such points exist. We have to show that there are such a thing. Well, if nothing else, at A is covered by its own interval, right? IA. So at least there's one point that is covered by a finite sequence of ICs, right? Okay. So next, let's say the A, if A is accessible, then if a point A is accessible, then every point to its left is accessible. Because if A can be covered by a finite collection, well, anything to the left can be covered by the same collection, so then it is also accessible. So, and therefore, right now we're left with two possibilities. Either every point from A to B is accessible, or there exists a point B, okay, which I have a picture here. And here there exists a point B such that every point to B's right is not accessible, and every point to the B's left is accessible. All right. So there's being that because of this situation, then we can move the point A to the right, keep moving it until it hits hits a stop, basically, where everything to the right to its left, behind it is okay, but the future is shot, basically, but the past is okay. So then we can define a B like this. Now, what is B? Now, would the big B be? There are two possibilities. Either big B equals to small b, so big B is all the way to the end, which means every single point is accessible, or you actually stop before you reach B, because only the first part is accessible, the rest is just int. Okay, so let's assume that is true, okay, that there's a big B that's smaller than the end point. If that is the case, then we're going to let delta equals to delta B over 2. Now, delta B is the covering at the point of big B, because we're given a bunch of covers, and we're trying to prove that we can pick a finite amount to cover this thing, right? So each point has its own cover, so IB will be the cover for B, and delta B is the width of IB. Now, so we're going to choose a new delta and define it as delta big B over 2. All right, so as you can see, IB extends over here, right? And then the delta goes halfway both sides. And then now we're going to consider the interval from A to B minus delta. So now we're considering this part. Now, what about it? Well, if you consider this part, it says that since B minus delta is to the left, then B minus delta is accessible. So then we can choose a bunch of stuff that covers all the way to B minus delta, okay? And then, and we call that IC1 to ICN. And then this thing is, then we have we toss in the IB, that is the cover that covers B. So we create a new collection with one more member, and one more cover, and that covers from A to B plus delta, right? And so it extends forward a little bit. Now, if that is the case, but that means that the points over here, B plus delta, is up in here are also covered, which is not true, which is not possible, because we already said that any point to the right of B cannot be covered, okay? It's not accessible. And as a result, we have a contradiction. Therefore, big B cannot be smaller than small b, and so big B is all the way up here, and that means the entire line is accessible. And that is a sample proof by contradiction. So please do this yourself, okay? This kind of proof will be used quite often in proofs of the continuity and this type. So it's good for you to teach yourself how to think this way. And so please be sure to do this yourself, okay? And think it through and make sure every step makes sense. And then we will go to the next part. Next, let's look at theorem 6 on page 171. We're looking at the bounded function theorem. That is, if f is continuous on the closed interval from a to b, then f has to be bounded. Put it another way, is the magnitude of f is less than some number m. Okay, and then as a counterexample is that if the interval isn't closed, let's say it's open from 0 to 1, and then we can quickly think of some simple example that will show that this function isn't bounded. In this case, 1 over x wouldn't be bounded from 0 to 1, okay? Because it goes to infinity as 0. And being that it's allowed to be on an open interval, it can just take off. And yeah, it's a goner. So we require for this theorem, we require f to be on a closed interval. Now, if this is the case, then we can find a bound for it. And so to prove that, then first we will do a quick trick for convenience. And so here's our function f, and defined from a to b. It might not be defined outside a or b, but to make our proof more systematic, we'll define after a to be whatever it was on a, and then after b to be whatever it was on b. Okay, so you have two level lines at the end. That way it's continuous everywhere. All right, so then next, let's pick a point C that's between a and b, kind of like this one. Okay, and then we are going to now f of x is continuous as c, so going back to the definition of continuity, that means given epsilon, we can find delta such that as long as x within a delta, then f of x will be within epsilon. Okay, that is a definition of continuity. And right now, we're going to choose epsilon equal to 1, which isn't much, right? So, but the same principle applies. So then we have by then defined in a cover at C. So the cover at C is defined as whatever x minus c is less than delta c, that will make fx minus fc less than equal to 1. See, x minus c is less than delta c. Now this is possible because f is continuous. That's the very definition of continuity. Now from this, we are going to get to this inequality, and so we'll prove that f of x is less than fc plus 1, and we'll define this value as m of c. Is that a c there? Yeah, I think so. And so that will be our our interval that will be corresponding to where f of x is in that little interval will be bounded by m of c. Now, how does these two inequalities translate into each other? As there's some quick algebra here. What happens is, this is what we're starting with, f of x minus fc is less than or equal to 1, and then this is the definition of the inequality, okay? That means it's between 1 and minus 1, which will move the 1 over or something, and then, well, this part is, so then we'll slap the f of c to the other side of the inequality. We end up with this, and then we'll slap ignore this part, and then slap the inequality sign on everything, okay? By the triangular inequality rule, that makes sense. If you slap it on there, then this will be less than equal to that, which is m of c, just like the book says. So that would be... So that's how the inequality translated from here to here. All right, so now we have, so with this definition, for each number c, we have defined a cover, I, okay? I is such that, to say it again, I is defined such that where, as long as x is, for epsilon is held at 1 for each c. So as long as x minus c is less than a delta, which is a positive number, then f and fc will have a value of less than 1. So for each c, we can do this because f is continuous, and as a result, we have a collection of covers, right? It might be infinite, it might be finite. We don't know, but it doesn't matter. Actually, it is infinite because we're doing this for each c in the interval from a to b. So now that we have done that, And well, this now we have satisfied the Heim-Borel theorem, right? Which says that to each C, well, our interval it has a cover for itself. It has an I, right, that covers each C from A to B. Then there exists points of a finite number of covers that will cover your entire interval. So then, okay, so we'll choose each finite cover, okay? And we choose a finite amount of covers that we'll call it IC1, C2, IC2, all the way to ICN, which covers the entire from A to B. Now, and each one, you notice, corresponds to a MC. Each one has a M on there where f of x is less than or equal to this big M. Now, as a result, let's pick so we have a finite number of stuff, right? Out of a finite number of stuff, we can pick something that's the biggest. So let M be the maximum of all the M's that we have found so far. And then at that point, then, being that each one is, each point X is inside some cover, right? Then each point X will satisfy this equation of, each point of f of x will satisfy this equation, which is less than the C, and then less than the big M, which is bigger than all the other M's. And that concludes the proof. Now, so please read this yourself, okay, and make sure that everything makes perfect sense. And then, and we'll go to the next theorem. Next, at the bottom of page 171, we're going to prove that if f is continuous in a closed interval, then f is going to be it will have a maximum, and not just that, there's some point from A to B that f will reach the maximum. That is, at some point it will become some maximum, and then at the other point it will be the minimum. That is, there exists a point C such that FC is equal to the maximum or minimum, depending on the situation. So let's look at turn the page where C is between A and B. This claim is false on the open interval. Why? Because the function f of x equal to x, it has no maximum on the interval, on the open interval 0 to 1. Now, why is that? Now, please think about that to figure out why that would be. You might think, well, isn't the maximum 1? No, because 1 is not in the domain, okay? We're not including 1, so 1 is not an option. We're talking about the interval from 0 to 1, not including 1. So what is the maximum of f of x equal to x? Now you don't know what to say, right? Because it has no maximum. How funny is this? So next let's look at theorem 7. Theorem 7, we have so we are gonna prove the what is this called? Achieving the maximum or minimum. Anyway, so let's say we have a function f that is continuous, and it is between a minimum and a maximum, right? And also, well, let me put it this way. Let's assume a function is continuous. Then there exists numbers, small m and big M, such that f of some number in C1 is going to be equal to small m, and f of some number C2 will be equal to big M. That is, there is a number that f will actually reach the maximum. So then, all right, so we are going to just prove for the maximum case, because the minimum case can be proved by applying the negative f of x, and it works the same way. It's just the other direction, right? And so let's prove the maximum. Now, by theorem 6, that we just proved that f of x continuous function on a closed interval is bounded, and therefore it has an upper bound. Now the next sentence, listen to the next sentence carefully. Let m be the least upper bound, okay, right here. So now that we know f is bounded, we assume there is a least upper bound. And that's because f is here, and we know it's bounded, so we'll take all the bounds, right? And we consider the one that's the smallest one. and we'll call that one the least upper bound. And so just, well, push this thing down until it touches F, right? And if there's still space left, that means you can push down a little more. So that thing, the least of all F's bounds, will be called the least upper bound. All right. So then in that case, for the least upper bound, we'll call it M. So now we're working with the least upper bound. Now then f of x is less than the M, right? The least upper bound, because even though it's the least, it's still the upper bound. So then we need to show that this equality holds for some kind of x in the interval a to b. Now, so we're going to prove this by contradiction. That is, assume that M minus f of x is bigger than 0. For the entire interval, okay? If that is the case, then we can define the function 1 over m minus f of x in the whole interval, and that function will be continuous, being that the function is bigger than 0 the whole time, right? So then 1 minus 1 over it, did I say 1 minus? 1 over the function is still continuous, and in there, m bigger than 0, or yeah, I think so, because it's positive. 1 over positive, still positive. Anyway, so then being that it is a continuous and function in a closed interval, it has to be bounded. But that is not possible because this function f gets very as close to the upper bound as it wants. The reason is because otherwise, m wouldn't be called the least upper bound, right? There can be a space in between. If there's a space in between, then f of x, then it wouldn't be the least upper bound. So being that it's the least upper bound, this function right here, that is the 1 over f minus 1 over m minus f of x, has become small. Just the denominator itself has to be arbitrarily small, which means this function cannot be bounded, and which creates a contradiction. And therefore, from that, we prove that it is possible for f to reach its maximum and minimum. So that is let's see. So the whole argument is roots on the fact that f can get as close to m as possible. As it wishes, okay? That is, given epsilon, doesn't matter how small, f can get, there's some point of f that's within epsilon of the least upper bound, and because that's the definition of the least upper bound. Okay, so that is theorem 7. So please think about these proofs very carefully and make sure and read them through slowly until the whole concept, your brain digests the whole thing well. Okay, so that is because these are more advanced concepts or styles of proof, and it might sound a bit confusing at first if you don't, but if you just stare at it long enough, you will get it. All right, because they're also quite intuitive. So next, let's look at the uniform continuity. I will finish this section in the next video. I didn't sleep enough last night again.